Alright, ladies and gentlemen, as we said yesterday or in the last talk where we stopped, we promised to continue giving the historical evolution of quantum mechanics. We stopped at Planck's radiation formula. Let me explain something more about that. The radiation formula treats electromagnetic waves as packets of energy, which Planck called quanta. So light is a wave as well as a stream of particles called quanta, quantum for one, hence the name quantum mechanics. And we said that Planck was forced to resort to that as a result of the problem that arose from black body radiation. Because we are not treating quantum mechanics directly, we are treating its historical evolution, so we don't need to waste much time on what black body is. After all, we have said a lot about it yesterday. So there was a concept called the ultraviolet catastrophe that happens in black body radiation. That was what forced Planck. So these scientists that developed modern physics were not rebellious to classical physics. No, they were trying to explain things in classical physics, and they began to observe things as instruments of observation kept evolving. So they were trying to explain things, and they found that some things could not be explained by the classical theory. So they were kind of forced into inventing new explanations. Then yesterday we talked about two models of the atom. That is the J.J. Thomson, that is John Joseph Thomson plum pudding model, and the Rutherford planetary model. And we said that Rutherford planetary model was not suitable because naturally, by changing angular momentum, the electron would be emitting energy in form of radiation, and continuous radiation actually classically. So it will finally spiral and plunge into the nucleus, and the atom collapses. But atoms do not collapse, especially, as I said yesterday, the hydrogen atom is one of the most stable systems in the universe. So who came to the aid of the hydrogen atom? It was Niels Bohr. He borrowed a leaf from Plancks that there are allowable energy states and forbidden gaps between the energy states. So the electron can orbit within an allowable energy state without emitting radiation. It only emits radiation when it makes a transition from a higher energy level to a lower energy level. And in that course, it releases a packet of energy, a packet of electromagnetic energy that is equivalent to the energy difference between the two levels. And when it makes a transition from a lower to a higher level, it also emits a packet of electromagnetic energy. As we said, electromagnetic waves are both particles, streams of particles, and streams classical waves, depending on the experiment or depending on your tools of experiment. So that was said by Planck, and it was enough an explanation. But to save the hydrogen atom, Niels Bohr had also resort to the fact that, to the postulation that angular momentum is also quantized. Well, quantized in the sense that it is in form of quanta. There are allowable momenta and forbidden momenta. So for whichever energy level, there is corresponding momentum, angular momentum levels, and in between there can be no angular momentum. Another thing is that angular momentum, yes, momentum is a vector, whereas energy is scalar quantity. Scalar quantity does not have direction. So for each energy level, if you at energy level 1, there will be 2 levels of momentum in opposing directions. So at energy level 2, there will be 4 levels of momentum. That is how Niels Bohr approached the concept, the hydrogen atom, and he gave close to a stable form of hydrogen atom. But from other emissions and some spectral lines, as instruments get improved, as I said, there were other orbitals that were discovered. One of them is spin angular momentum. It is pointless to think of the electron as something rotating because it is assumed to be a point particle in this case, but the spin is an intrinsic property of the electron. So in one energy state, there can be 2 electrons, one spinning up and the other spinning down. The spin can either be -½ or +½ or -1/2 or +1/2. We are not actually talking about quantum mechanics in itself. That is why we are not even writing. We are just narrating the historical development of this field called quantum mechanics. So the players after Planck, then we have Niels Bohr. Wolfgang Pauli is one who suggested the spin of electron. Then another scientist, a French scientist, Louis de Broglie. He is called de Broglie, but mostly his name is mispronounced as de Broglie because it is B-R-O-G-L-I-E. But in French, that is de Broglie, Louis de Broglie. Louis de Broglie thought of some things, especially symmetry in nature. He considered that, okay, there is radiation, there is matter on one hand, and there is one concept in classical mechanics known as the least action principle. It applies in quantum in mechanics as well as in optics. So this symmetry in nature and the fact that light is a packet of energy particles as well as waves led the Bruyn to think that, okay, why not matter also exist in such two states, wave as well as particles. So it was Louis de Bruyn who first suggested the concept of matter waves. The concept of matter waves was proved by one kind of experiment known as the double slit experiment. This is known in classical wave theory, but it happens with electrons. When you have a screen in which you have two slits and an electron gun, that means an electron emitter. It may be a thermionic emitter or photoelectric emitter whatsoever. It emits electrons with certain kinetic energy that will enable them reach the screen. I mean, before the screen you have a barrier. In that barrier, two slits are provided. So it appears as if the electron goes through both slits at the same time. First, when you begin to shoot the electrons frequently, you get exactly the picture that you get when you pass waves through double slits. You have peak at one point, that is the maxima, and you have other lower amplitudes. That would like say, okay, the electrons are coming in many in copious amounts. So someone decided to, okay, shoot one electron at a time, one after another, and when they piled up, they still gave the same result, a maxima at one point and other smaller amplitudes. This is the behavior of waves. So in this case, electrons behaved like waves. So that was extended to other small particles, not smaller than electron actually, but tiny particles like protons, neutrons, and even some molecules are found to behave that way. So this established the fact that matter can exist in either wave form or particle form. That is what is called the wave-particle duality of matter, or wave-particle paradox. Then Erwin Schrodinger used this concept and built an equation which became the counterpart of Newton's second law, force is equal to mass times acceleration, or an equivalent to rendition of Newtonian mechanics in analytical mechanics known as Hamiltonian total energy expressed in terms of waves. It is called Schrodinger equation. One equation is time dependent and the other is time independent, but they both describe the Hamiltonian of a system, be it an atom, an electron, a molecule, or even if something bigger within the range of frequency that can be treated quantum mechanically. So in that case, we still have another contributor known as Werner Heisenberg. Werner Heisenberg stated that there is uncertainty in observing either position, energy, momentum, or position of a particle. So it goes this way. You cannot simultaneously measure the position and momentum of a particle simultaneously, nor can you simultaneously measure the energy and time of a particle. This is known as uncertainty principle. This uncertainty principle has deep implications into physics, because, for instance, in thermodynamics, if the uncertainty principle does not apply, which means you would know the position of an object and its momentum at the same time, it means the particle will have zero momentum. Zero momentum means zero motion. It should be stand still. Then you would know the position, and knowing the momentum is zero. But when momentum is zero, everything collapses, because that is the attainment of absolute zero temperature. So we can say that it is the uncertainty principle that bars objects from attaining absolute zero temperature. It can be extended to the fact that, okay, the entire universe might even collapse if one system collapses under the uncertainty principle. That is a contribution by Werner Heisenberg. So let us still go back to Schrodinger equation. Schrodinger equation gives a solution of like wave. So the wave function of a particle has no meaning in itself, but the amplitude of the particle, of the wave, at any point x along, if you like, the x-axis, determines the square of the amplitude, determines the probability of locating the particle at that point x. So the higher the amplitude, the higher the possibility of locating the particle there. Then we take this back to the atom again. The least energy level given by Niels Bohr is at a distance r, or it is normally called a. It is called the Bohr radius, but it's a kind of function like the probability normal distribution curve. So the peak is the Bohr radius, and it is at that point that we expect most likely that the electron exists there from the proton. But uncertainty principle gives it more time. More chances that it can be of lesser amplitude. Having lesser amplitude means that, okay, so there is the concept of electron cloud around the nucleus. Uncertainty principle gives it, makes it possible for an electron to be less than the Bohr radius from the nucleus. So there are a lot of contributors. In summary, let us list some of them. We have Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, Paul Dirac, Wolfgang Pauli, Louis de Bruyn, Erwin Schrödinger, Max Born, Arthur Compton, Ernest Rutherford, Enrico Fermi, and J.J. Thomson. This has nothing to do with any chronological order. Thank you very much. Don't forget to subscribe and hit the notification button. Thank you for listening.